Righty, this video is just going to explain section 2.1 titled Consistency and Uniqueness of Solutions, and I'm going to pitch this at merit level of understanding. Okay, so if we follow the script here, let's see if this works. Yep. Okay, so it says look at the theory on pages 24, and here it is, page 24. And obviously, it's pretty straightforward. You're seeing two parallel lines. Well, what's tricky about it is, it's not the structure y equals mx plus c. So then it would be obvious they have the same gradient, but they have a different y-intercept. So this top equation here looks like it has a plus 3 y-intercept, and this one down here, I don't know, negative 0.5 y-intercept. But they have the same gradient. They're like parallel lines, railway tracks that never cross over. Okay, so the key thing is if you had these equations and you did the algebra to eliminate them, as you've been doing previously, you would get something strange. Okay, now let's just zoom in here. And what you get is a contradictory statement. For example, doing the algebra, taking equation 1, times it by 2, you get this. If you add 2 and 3, boom, 0 does not equal negative 28. That's a false statement. That's the word I use, actually, false statement. So what you've just done there is prove that this is, what's the word? Inconsistent is the word, okay? Whereas if the equation, this bottom equation was cutting through here, there would be an intersection point, and you could say there is a unique solution. This is two-dimensional. Boring. What we need to do now is basically switch into examples on page 25 and 26. And let's just scroll this way, please. Are you working for me? Cool. Okay, so what you've got here is two planes. Let's put a third plane in. And wow, what do you notice here? What you're looking at here is also a scenario, and this is from a GeoGebra. GeoGebra, whatever. 3 planes, and obviously what you're seeing here is not a unique solution. So this case is going to be inconsistent. And if you look at this page here, it talks about scenarios where you've got 2 parallel planes and another plane cutting through. So the solution set is where the planes intersect, and there's an infinite. Well, there's no clear solution set here for those 2, but for all 3 equations, there's no possible solution set. Another scenario, the planes are all parallel. There's no solution set. There's no value for x, y, and z that could satisfy each of the 3 equation planes. Right, and the key thing to consider is you'll get a error statement on your calculator. Okay, let's just click on this page here. And so if the calculator is giving you an error, you need to actually show why it's an error. You need to do the algebra for it and get this contradictory or false statement. So here's a good example on page 26. You've got the 3 equations, 1, 2, 3, and look at Bluey here, telling you what to do. Looks like Bluey's saying, hey, take equation 1 and times it by negative 2. That gives you that, which is equation 4. Place underneath it equation 2, and then go, hey, 2 plus 4. Why are you doing that? Looks like you're going to eliminate x. What's left over? 3y. What's this? Minus 5y equals 23, and that's equation 5. Do something with, what's it saying here? Combining equations 4 and equations 3. So take that one, and you eliminate things, and you get this statement. So then it's going to say, look at equations 5 and equation 6. If you take, let's take equation 5 and multiply it by negative 2, gives you this. If you add these equations, what do you notice? You get a contradictory statement. Now, here they decided to, in this example, eliminate x. You could have decided to eliminate y or z, and your algebra working would result in a different contradictory statement. Say that again, a different contradictory statement. You might get 0 equals 15. or 0 equals 92, whatever. But the key thing is, don't assume that's an answer. No, that's not an answer. That's a false statement. 0 does not. So as long as you're getting any sort of false statement, you're proving algebraically that those three equations are, here's the word, inconsistent. And here's your challenge. If you were to take those equations there, go into GeoGebra, I think I pronounced it correctly then, you should see this. Now, there's a wee challenge for you. Get the page open and put that in, and you should see this. Is there any way there's going to be a unique solution in there? No. Okay. So hopefully that's helpful. Let's go back to the notes here. Right. To supplement your New Lake, do look at this here. These are really good. This one here, types of equations. Let's open that one up. Okay, it does look scary, 59 pages. Don't forget, each one's just a slight click. And again, starts off with two-dimensional here. And okay, let's just stop at this point. Yeah, so if you get a unique solution for the three planes, there's one point where the planes are crossing and they all share that exact point. And that the coordinates of that point would fit in each of the three equations. Yeah. Okay. What you're looking at here, ignore the second bullet point. That's coming. That's the E-level stuff. But when the equations are what? Inconsistent is what you're trying to do here. So then it goes through. Look, here's a unique solution. This one here. So it says if you were to plug in 3, -1, and 4, it would appear right there. Hey, we challenge, take this information here and plug it on to GeoGebra. You'd see this. You can change the colors so you get the same colors. And if you typed in as a coordinate point 3, -1, 4, it will appear literally right there where the intersection of those three planes are. So that is a unique solution. Righty, so great PowerPoint this, flick through, then it goes on the second scenario where equations are dependent. Now this is what we're going to cover in section 2.3. And this, by the way, ladies and gentlemen, is your E-level stuff, where you get an infinite number of solutions. In fact, let's just put, you can't type it in there because it's view only. You get an infinite number of solutions, okay? So anywhere along here, the points will work for green, blue, and red equations. Okay, here's a scenario, three parallel planes, there's no solution. Okay, this one here, there's no solution because, yeah, where that blue plane intersects these planes, there's infinite number of positions where it can intersect, okay? Keep going. Scenarios inconsistent, no solution. And here are some examples of equations which you could place into GeoGebra and visually see these results here. Okay, great PowerPoint there. Go back to here, another really, okay, this one here is more detailed, and this is the focus for obviously 2.0 here. Consistency and uniqueness of solutions. Maybe I should add to the title here, inconsistent, but consistent or inconsistent. Consistent means there is a solution possible. Inconsistent, not one. Okay, so do look at this PowerPoint and it gives you a really clear example of that. And lastly, you should do all 45 to 50. And I've got here 3 problems. And don't forget, the new regime now is the red boxes. I would like you to have a good honest attempt at 46 and 48 and insert the image of that in that page there. And I can look at it and straight away, get a feel if you're coping with the content. Hope this helps. We will be talking about this. In fact, I may even do an example in front of you in the VC session on next Wednesday. Alrighty.